Well, all right, here we are. So I guess, I don't know about where you are, but up here, we didn't get a whole lot of snow. They're making it sound like it was going to be a massive, massive blizzard or something. And well, not really, but that's okay. It's not the worst thing in the world to have a class online once in a while. So what we need to do today is go over the second of the two chapter 11 problem sets. And then as much time, with whatever's time is left over, we can work on the sample midterms. So, because remember, next week, a week from today is March the 4th, and that's when we plan to have our midterm. That way you've got plenty of time before spring break. And so why don't we do this? Hopefully you have your calculators ready because we're going to need them. So here we go. So you can tell right off the bat that this is a different type of problem than what we were doing in the first problem set. Right? I mean, you can see there's a table here. There's a reason for this table being here. They're giving us the raw data for this experiment. A new drug is being tested to determine if it lowers cholesterol. A sample of 8 volunteers is chosen. The cholesterol readings of them volunteers taking the drug before and after are shown in the table. Now, here I very kindly given you the differences already. All right. If they're not there, you have to do this yourself. And remember, the differences are defined as the before readings minus the after readings. So in this case, for example, 144 minus 139 gives you a 5. Now, this is exactly what the drug company was hoping to see. Positive differences are good because that means that the cholesterol is going down. All right, that's the purpose of this pill, to lower cholesterol. So we want to test the hypothesis that the mean readings are the same before and after, but because of the way this is written, this will be a right-tail test because of the fact that we're hoping that the readings are going down, which means that we have positive differences. So why don't we start out by writing out the hypotheses. So remember, with this type of test, the notation is slightly different. We're going to call this mu d equals 0, where mu d, if you recall, is mu1 minus mu0, minus mu2. And so the alternative would be that this difference is positive. That's what we're looking for evidence of. Strong enough evidence that we can actually promote this drug in the marketplace and say, yeah, our evidence shows that it worked. People's readings did go down. Now, alpha is 5%, which is so often the case. So here's what you have to do. Now, we've got a few options here. Remember, the test statistic is a little different than what we're used to seeing. T equals D bar over SD over radical N. Now, there is a formula for calculating D bar and SD, where D bar, by the way, is the mean difference. And then SD is the standard deviation of the differences. Specifically, the sample standard deviation, of the differences. Now, we know that this isn't, we can do this ourselves, but there's a trick that will avoid the need for this. What is that trick again? All right, well, here's what we can do. If you go to your lists, okay, now the lists are found on your calculator by hitting Stat, Tests, and then just leave it at the first setting, which is Edit, Stat, Tests. Actually, no, sorry, what am I saying? Yes, it's not Stat Tests. It's Stat Edit. We're so used to using Stat Tests that I automatically said that. It's not tests, it's Edit. The first one, you see it right there. In fact, if you look at the top of the menu, it has Edit, Calc, and Test to choose from. So we'll leave it in the default setting of Edit, and then choice number 1 is also Edit. So if you pick that, that will bring you to the lists by hitting Enter. Now, if we didn't have the differences here, you would be asked to calculate or enter these numbers into list 1, and these could go into list 2. And then you would let the calculator calculate the differences. Okay, we saw how to do that in class, but because the differences are already here, what you can do instead is simply type the differences in list 1. Okay, so what we're going to do is enter the differences in L1. Okay, and then when you are done, hit second mode to leave the list mode. Don't forget about that. And also, before you get started, I strongly recommend that you erase all the old data. I'll make a note of that here too. To erase old data, go to the top heading of the list and hit clear. Okay, which is way over in the far right corner of the calculator. All right, so let me scroll this back up again so you can see it. So why don't you go ahead and take a minute and enter the differences into your calculator. In list 1, that is. Now, it doesn't have to be list 1. I just think it makes the most sense. You have to be careful. You want to remember where you're keeping all your information. So go ahead and type 5, 5, -1, 7, 3, -3, 7, and 4. When you're done, like I said, you can hit second mode. So all the information is in your list. And what we're actually going to do is ask it to calculate D bar and SD. And then we'll plug it in ourselves into the test statistic. Okay, so in other words, and how do you do that, by the way? All right, hold on one second. Let me split the screen in half. So the calculator can then calculate the mean of the differences, or the mean and the standard deviation of the differences, as follows. So you would hit stat, and this time when you hit stat, you're using the middle menu, which is calc. And then you're going to choose the first one, which is 1 var stats. And when you do that, make sure it knows that your list is L1. Now, if it's not already L1, what you have to do is hit second 1. This appears as L1 on the calculator. All right, so the second puts it into, tells it that you're looking at a list, so second 1. And then everything else, just leave it, hit calculate. And then what it will do is it'll produce a list of statistics based on that data. So the first one, X bar, is what we're calling D bar, which is 3.375. And then the statistic that it's calling SX, what we're calling SD, is about 3.622. 228, let's say. Okay, and of course you know already that n is 8 because there's 8 elements in these 2 samples. Okay, so that means we can now take this test statistic, and fill it in ourselves. Oh. All right, there we go. All right, and then of course, remember n is 8. In fact, it may even say that in there somewhere. Yes, it does, as a matter of fact, in case you forgot. N is 8, that's also listed in there. So let's do this. 3.375 over 3.6228 over radical 8. And that's going to be approximately 2.635, let's say, depending on how many digits you used. 2.635 is the test statistic. Now, the critical values are easy in these cases because we're treating the differences as a single sample. So you would simply have critical value with a right-tailed test, T alpha, and the degrees of freedom is very simple. It's n-1. So you could go look at the table if you want to. In fact, let's do that. Let's go get the table. Hold on one second. But you might be better off using your calculator in this case. 7, the tail area is 0.05. We have 7 degrees of freedom. That means we're looking at this table, this column. And there you go. With 7 degrees of freedom, we're looking at 1.895. Or, of course, there's always an or. There's always another option, I'm sure you've noticed this. There's always multiple ways of getting at any result. So what we can do instead is you can go to second vars and selection number 4 is INVT. And when you choose INVT, it really only needs 2 things. It needs an area and it needs degrees of freedom. Okay, so because we're looking at the right tail, whatever this number is, 5% is in the right tail. Which means it's 95% is in the left tail. Okay. Now, if you have a different calculator, like these TI-84 CE series, you can actually ask it for left or right tail. But with the 84, the basic 84, it defaults to left. So for area, you should choose 0.95. And degrees of freedom, as we've just seen, is 7. And then go ahead and ask it, what number are you giving me here? 0.95, 7? And it's given us about 2. Oh, no, something went wrong here. I made a typo, sorry, hold on. Okay, after all that, yes, I made a typo. Yes, I mean, we know what it has. No. Oh, that's right. It says 1.89. That made me nervous for a second. 1.89. 457. So yes, 1.895 is fine. Okay. That's our critical value. Now, by the way, if you used 0.05 in the area, just a quick reminder, it would have given you negative 1.89457, and that would be your sign that, whoops, you got the wrong tail, but it's the right number. Okay. Now, the test statistic is 2.635. So that tells us that the test statistic is out in the rejection region. And yeah, 2.635. This is our test statistic. And the fact that it's out there in the rejection region, yeah, let me make it a little bigger. I know that from experience with Zoom, that whatever I'm seeing here, you're probably seeing a smaller version of it on your screen. So I want to make sure that you can read it. If it starts to become awkward to see it, you have to just let me know and I'll make it bigger. Okay. All right. So since the test statistic is in the rejection region, you reject the null hypothesis. proves that the mean difference is 0 and accept the alternative that the mean difference is positive. This means that the drug is effective. I don't remember if they asked us that or not. Let's go check. No, it just says test the hypothesis, but if you were asked for a conclusion, that would be your conclusion. The drug does work, or at least we have evidence to suggest that it does. All right. It's still, I mean, it doesn't guarantee anything. It's still not 100%. There's still a chance that we inadvertently picked 8 patients who were more likely to respond to the medication. Who knows? So there's always a chance, and we know that, but it looks like the drug works. Okay, now, what if we wanted to use the p-value approach? I think everybody prefers the p-value approach, but that's okay. We're going to do both just because I really want everyone to understand what we're actually doing here. So I just want to quickly remind you that when you use the p-value approach, what you're actually looking for when you get your answer, what you've actually done is you have calculated the area in the tail that is in excess of your test statistic. And you can see it's going to be a fairly small number, which makes sense because that is why we will be able to reject the null. Okay, so all right, so let's go to your calculator. This time you'll do stat tests. Use, surprisingly enough, t-test, because we're treating the differences as a single sample. Okay, and now what you can do, since we do have the summary statistics already, you can use the stats mode if you choose to do so. And if you do, you would fill in, boy, I completely forgot that we actually have 2 more options here. mu0, which is what we're calling mu d, is 0. X bar, which is actually d bar, 3.375. Now, if you noticed, your calculator is smart. In my case, at least, it's already plugged those numbers in because that's what we got from our last set of calculations. So I don't even need to retype these numbers. That's kind of cool, isn't it? It's like saying, oh, do you want to use the results from your last round of calculations? If so, here they are. 3.6228. And then n would be 8. It's all still there. Wow. And then don't forget to remind it, though, that this is a right-tailed test. All right. All right, choose that, calculate, and it'll come back and you'll confirm a lot of things that we already knew. For example, it'll remind us that the test statistic is approximately 2.635. It's giving us the p-value that we were hoping for, 0.0168. It's also giving us back the X bar and the SX, which we already knew, but the important detail is this one. P-value is less than alpha, so therefore we reject the null. But the mean difference is 0. The alternative is what is accepted. So that means the drug works. But what else could we have done? Since we went through the trouble of entering all this information, we might as well take advantage of it. Suppose you had done this, stat tests. Number 2, t-test. Instead of asking for stats, you could have asked it for data. because it's already there. It's in the list. So go to stat tests, t-test, switch the menu over to data, and just make sure that it knows that, oh, you still need the null hypothesis. But what you would then do is say, oh, listen, all the data that I've generated is in list 1. So list, make sure it knows that you're in L1. And don't touch the frequency. It doesn't like that. Just leave it. And then, of course, on my calculator, it remembers that I've used the right tail test recently, so it's keeping it there. And then just hit on calculate. And it's all the same information, isn't it? Yes. It'll give you the p-value of 0.0168. Man, look at all these choices we have. So you can do whatever it takes to get this done. So in other words, you have at least 3, maybe 4 different options here. Any way you look at it, though, we rejected the null. And that's the bottom line. Wow. Pretty impressive. This calculator is pretty smart. Now, here's another one. Now you can see it's a very similar problem. So you can decide for yourself which of these approaches you want to use. And once again, we have the difference. So you don't have to type 2 columns into your calculators. And so what do they want to know? We're trying to find out if the average spending per household on a specific product has increased after a major advertising campaign. We randomly pick 6 households and we compare their spending before and after the ads have run. Now, in this case, if the spending goes up, the mean difference will actually be negative. So therefore, we must be testing a left tail test here. Okay, left tail this time. Because instead of hoping that the numbers went down, we're hoping that they went up. And this time, ooh, we got a little monkey wrench thrown into our plans here. The alpha is 0.01. All right, so here's what you should do. Go to your list and enter the differences. And be careful because this time there's negatives and there's fractions. So no more integers. So let's go back to the list. You can clean out, or if you don't want to take them out of there, you could go to L2 if you want. If you want to save the work for number 1. Doesn't make any difference to the calculator. All right, let's take a minute and do that. Okay. Okay, so I'm going to get out of the mode now. All right, so just like before, there's a few options we have. We can try to calculate the test statistic ourselves by using its function calc. Okay, so the calculator can calculate the values of the average difference and the standard deviation of the differences by entering the data, the differences that is, into a list and then using stat calc. So we hit stat calc. Number one is one var stats. And it's already done. Just hit it. You don't have to do anything else. Oh, except to remind it what list you want. Okay. And then everything else, leave it the way it is. Go to calculate. And let's see, what have we got? So it's coming back with an X bar or D bar, I'll put in parentheses, of 2.108. No, try to make this as neat as possible. Not like writing on the board, that's for sure. All right, there we go. And then SX, you can read it from a little further down. About 4.48, 35, let's say. That's fine. And then N, if you forget, is 6. It's down in the bottom there. So the test statistic will be all right. And so that should give you about, let's say, about negative, wait a minute. Oh, hold on. 1.15 once, approximately. You don't have to use that many digits, but about 1.15 is fine. Okay, so it's a fairly small number. So it doesn't look like we're going to be able to reject the null. Now, the critical value, since it's a left tail test, negative T alpha over, alpha, not alpha over 2, alpha, and minus 1 degrees of freedom. Remember, this time we chose 1% though. Don't forget about that. It's easy to get into the habit of thinking it's always 5%, but this time it is 1%. Because it just usually means that they're looking for extremely strong evidence that this is, we can reject the null. There's some reason why we have to be extra careful. So, so once again, we can look this up in the table. Let's see. This time there's only 1% in the tail. There's 5 degrees of freedom. So we're going to have actually negative 3.365 because we're in the left tail. Or, of course, second vars, number 4, INVT. And this is a left tail test. So therefore, the error should be 0.01. With 5 degrees of freedom. So if you type that in, let's see, 0.01 with 5 degrees of freedom, it should give you negative 3.365. That's fine, perfect. Okay, so that's negative 3.365, but the test statistic it's like way up here somewhere. It's not even close to the rejection region. So since the test statistic is not in the rejection region, we do not reject the null hypothesis that the mean difference is 0. This shows, if they ask, this shows that the advertising campaign did not, or I guess what we should say is that this shows that you have to be very conservative with these statements. There's insufficient evidence to show that the advertising campaign led to higher sales. All right, so that's that. Now we get to try our hand at the p-value. All right, so we go to second vars t-test. And again, here we can do this in two equivalent ways. So we'll go to second t-test. Oh, sorry, wrong one. Sorry, stat, my fault. Stat test. That's better, right? Okay, so we can do stats if you want. If you use stats, because you know the stats, you've got mu0 is 0. Leave that at 0, of course. And then it asks you for X bar. If you notice, it's already there. How does it know that? Because we just got through calculating these numbers and we haven't done anything in between. So in other words, as soon as you did the one bar stats, it keeps track of those numbers and it fits them into whatever test you do next. So you don't even have to bother typing these in. It's already there. Okay, so X bar, SX, man, that is helpful. 4.4835, and then N is 6. Make sure it's a left-tailed test. And then calculate. Okay, and then you go in here and you'll see that it repeats for us the t statistic or test statistic, which you already knew to be about 1.15. Okay, they've ran it a little differently. They've got it as 1.9, but it doesn't make any difference. Yeah, that's fine. It's because of rounding. And then the big result we want 0.84. Wow, that's a big p-value. And then the rest is just a repeat of what we've seen. So since the p-value is way above alpha, do not reject the null. That's it. Okay, and you can see why, because the p-value is actually the entire area to the left of 1.1516. It's enormous. Okay, in fact, maybe we could grab this just to illustrate how big this really is. So it's gigantic. Okay, and then of course, the other option we could have used is to say, well, all right, we're going to go back and use stat tests, but this time instead of stats, we're going to use data. Because this time, all it really needs to know is where the list is. Okay, well, you have to specify the null hypothesis, but then it's going to say, well, all right, where is this list you're talking about? And then you leave the rest, make sure that it knows that this is a left-tail test. And you calculate, of course, and you'll get the same thing. And it's just the same conclusion, do not reject. And so that means that they're going to have to try something different. Okay, the advertising they're trying now just isn't doing the job. All right. Let's say the ad is so obnoxious that nobody wants to buy the product. That happens. You know, just because something's on TV doesn't mean people are going to go for it. Yes, some commercials, as you know, are very successful and some of them are catastrophically unsuccessful. All right, you can tell because it disappears very quickly. Same thing happens with the TV shows. If they stop showing it after 5 or 6 episodes, something went horribly wrong. All right. Now, this one is different because we're no longer looking at means. This is the proportion. We're looking at the proportions among men and women. This is a 2-proportion test. And we want to know if the proportion of retirees is the same among men and women. Okay, so let's see. Well, in the real world, it's not going to be the same because, as we know, women tend to live longer than men. So probably there'd be more retired women. But for the purpose of this problem, we've got 80 men, 90 women. Among the men, 5 are retired. Among the women, 8 are retired. So that means the sample proportion here is 5 out of 80, which is, let's see, about 0.0625. And here, that means the sample proportion, 8 out of 90 is approximately 0.0889. All right, so we're trying to find out if it's the same, by the way, yes or no. So that means it's a 2-tailed test. So remember, we're using pi to represent the proportion of a population. And somewhere along the way, it tells us that alpha is 0.05. Now, the test statistic. And by the way, we can't use lists in this case because we don't have the original data. We only have the summary statistics. It would be nice. The lists are pretty cool, but that really only works if you have the original numbers. So instead, though, we've got a lot of other choices or a lot of other options. So remember, the test statistic is this scary looking thing. Wow, look at this. And then that P bar stands for this. It's a weighted average of the two proportions. So of course we have to do that first before we can plug it into the test statistic. All right, so P bar would therefore equal, we need it from up here. 8, let me split the screen here. Don't want to scroll back and forth 800 times, that's for sure. Here we go. All right. So 0.06, sorry, N1 is 80. 0.0625. 90. 0.0889. And then we divide by the sum of the two ends. And when you calculate that, that works out to be about 0.0765. Now, with that being said, we can figure out the test statistic. In the numerator, we subtract these two. Ooh, this one's tricky. So we have 0.0765. And then this will be 9 to 35. 1 over 80. 1 over 90. Now, that's a very messy expression. So let me just tell you what that worked out to be. It's negative. You can see it's negative, but it's only negative 0.646. Oh boy, that's a small number. So it doesn't look like we'll be able to reject the null. Okay, but we still need to go through the formality of calculating the critical values and confirming this. And as usual with the standard normal, it's just plus and minus z alpha over 2. Alpha is 0.05 in this case. So what we're looking for, and we can do this either with the tables or that special function, INV norm. Okay, so if we looked in a table, let's get that table. All right, so what we're actually looking for is the area below this upper limit. Everything below this is a total of 0.975. Now we can find in the body of the table, it's here. We don't have to round this one. There we go. 1.9 and 0.06. So this is 1.96. And that implies that the other one must be negative 1.96. Okay. But you can see the test statistic isn't even close to either one of those. Let's draw that again real fast. Oh boy. And so we ended up with negative 0.646. So it's not even close. So what this means then is that since the test statistic is not in the rejection region, we do not reject the null hypothesis that the mean proportion, I shouldn't call it that, the proportion of retirees is equal among men and women. So, all right, well, that's that. Now we can also, of course, and by the way, of course, over here, you could also have looked this up with second vars. Number 3 is INV norm. And when you choose INV norm, you only need 2 things. Well, you need 3 things actually: area, mean, and standard deviation. Area would be 0.975. And then these would be 0 and 1 because it's standard normal. And it would, of course, have given you the same thing. But maybe we want to use the p-value. That's cool too. We like the p-value, it's fun. So let's go to the calculator. Second vars, and oh no, sorry, not I keep doing that. Stat tests. This is 2 prop Z test. It's, and remember too, proportions, you always use the standard normal. So the only thing you have to think about is how many populations are we comparing? Is it 1 or 2? So in this case, it's 2. And this is actually number 6. Okay. And again, I mean, it's possible if you don't have the TI-84, if you're using a slightly different version, maybe the CE version, for example, or if you have one that's more advanced, there might be small differences between what I'm showing you here and what your calculator does. So you have to get that straight right away. All right, then. Now here, it's going to ask you for X. Oh, you know what I need to do? Split the screen. I want to be able to see, yeah, these numbers. By the way, if you're using Word to write your term papers and stuff, I'm hoping that you'll pick up some tips from watching this too, because there's a lot of cool features in here that you might not know about that can make your life a lot easier. Yeah, one day maybe we'll go over that in class, but all right. So they're asking for X1, which is 5, N1, which is 0, X2, 8, N2, 90. And then, of course, it's a two-tailed test, P1, unequal. Now here's one of the things that you should know about. The unequal symbol. Where do I find that? Well, there's a symbol box. And by the way, if you're using a Mac, yours might be a little different. Symbol. Now, since I use this all the time, it's already there. If it's not there, here's a cool trick for finding your not equal symbol. You can go to the symbol box, but it will take you the rest of the week to find it because it's so poorly organized. So here's what you do instead. Here's a helpful hint of the day. Every one of these characters has a code attached to it called Unicode 2260. Watch what I do here. If I couldn't find it, I just typed 2260, and on the PC, it's Alt X. Oh no, it didn't work. What happened? There it is. The space threw it off. Okay, if you type Alt X after typing the Unicode symbol or code, you'll get your symbol and you don't have to mess around with the box. All right, so again, suppose you're writing a paper that involves a lot of symbols. Well, now you know what to do. All right, so pick P2. Make sure it's a two-tailed test. So, oh, what did I do here? N1 is 80. All right, that's better. All right. So go down here. Make sure it's a two-tailed test. Calculate. The p-value is 0.5181, which shouldn't surprise you, given how small the test statistic was. When it's that small, that implies a very large p-value. Okay, so for the same reasoning, since the p-value is greater than alpha, we do not reject the null hypothesis that the mean proportions, are equal. Okay, so that's it. Okay, well, that was fun. See, now we can start looking at the sample midterm. At the very least, we can go through the fill-ins. I don't want to waste any time because, let's face it, the next Tuesday is our last day that we can review if we want to have this test on time. And we do, don't we? Yes. All right, so let's go grab that. And of course, I will post these solutions on Blackboard. And that way you won't, you haven't missed anything. Plus, there's a recording going on too. Don't forget about that. Since we're online, it's being recorded and you'll have access to that. Not on Blackboard, or actually maybe I could put it on Blackboard, but if not, I can stick it into my YouTube account because these videos take up a lot of space. And sometimes it's just too much to put on Blackboard. So I'll let you know about that. All right, well, anyway, let's go open up the test sample midterm rather. And you can see there's a bunch of problems, but first we have all these fill-ins. Well, it's actually not as many as I thought, but okay, well, let's at least get started on this. All right, now here's a classic example of a fill-in. It's a question in English. A type 1 error. This means rejecting the null hypothesis when it is true. Now, because this is English, we've got some leeway here. Anything that makes it clear that you understand that we've rejected the null when we shouldn't have, that's okay. All right. What is a null hypothesis? A statement that is assumed to be true unless there is strong contradictory evidence. Okay, so we start out with that as our assumption, and we continue to live with that assumption unless we find evidence that it's false. All right, when conducting right-tail hypothesis tests, what is the alternative? Okay, now here, yeah, this one is not as clear as it should be. It should have said about the population mean. I'll try to make sure that that is correct on the test. So what it really is asking you is this: how do you write the alternative hypothesis? Okay, so because it wasn't clear though, I want to make it, make sure you know, it meant when you're testing a hypothesis about a single population mean. All right. And if that happens during a test, you can always come up and ask. All right, if a small sample is used, what is the test statistic? See, this time it does say for the population mean. Well, that was a good idea. So remember, well, this one actually needs to be fixed too, but the intention here, and I'll I'll make sure this is clear on the actual test. I will make sure that you don't have any issues. The idea was just to ask you which test statistic to use. The small sample, the thing is about small samples is normally we use T with small samples because it's very rare that we actually know the population standard deviation. With larger samples, it ends up not really making much of a difference whether you use T or Z. It's really the small samples where T is important. Okay, but this is not written as well as it could be again, so I'll fix that. And I will double check the exams before I Xerox them. All right, now what's next? What sample size is considered to be large when testing a hypothesis? All right. So remember with the central limit theorem, you were told that we make a distinction between small and large samples. A large sample is one in which the sample size is 30 or more. Okay, so the cutoff point between large and small is 30. For a two-tailed test with a small sample. All right, so again, the theory here is that we're supposed, the idea is you want to give it plus and minus T, and I really have to rewrite some of these. This was supposed to be a single population mean. Okay. So in other words, all I wanted to know is how do you write the critical values in this case, plus or minus T and minus 1 alpha over 2. All right, now if the p-value is less than the level of significance, is the null hypothesis rejected? Yes, okay, that was easy. All right, what's next? Oh, now this is where it gets a little tricky. You be careful with this one. The level, now remember the level of significance is alpha. All right, so alpha is the level of significance, which refers to the probability of a type 1 error. Now, you don't have to write all this explanation. As alpha increases, the probability of a type 1 error increases, which means that the probability of a type 2 error, which we sometimes call beta, must decrease. Okay, so that's the logic. When you write this down, you can just say decreases, but I want you to know why. All right, so we went over this in the very beginning of the course. There's a type 1 and a type 2 error. To have less of one, you must accept more of the other. You can't lower them both unless you change the sample size. But if one goes up, the other has to go down. So that was the point of this question. Oh, now this one, remember all those cases we saw when we have a hypothesis test about 2 means, which is the only case, remember when we're dealing with the 3 independent sample cases, 1, 2A, and 2B, which is the one when we were allowed to use the standard normal? So that was the one when the populations are independent. The population variances are not equal, and the sample sizes are both large. Okay, so this is what we call case 2B. Okay. So if you look at the list, there's 3 of them. One, 2A and 2B. One was the one where the population variances are equal. 2A and 2B are the ones where they're not. And within that group, we have to know if the sample sizes are large or small. All right. Number 10, when testing hypothesis about two population means, when the populations are not independent, then we always use the t-distribution. Okay, so this is the last case, the one with the tables. Okay, we're comparing, patients who took a drug to help lower their cholesterol, that kind of thing. Those tests are always based on the t-distribution. All right, so that's done. Now here you've got 6 more hypothesis tests. So what we'll do, let's at least take a look at this one. What's going on here? Let's at least set it up. We want to make sure the orange juice contains at least 50 milligrams. Because if not, the manufacturer will have to use a more expensive type of orange in its production process. Let's say they're using inexpensive oranges and they want to make sure that they don't need to go and get the more expensive ones. Let's say they're using Florida oranges and they may have to buy them from Spain or something. So what we're trying to find out is that if the mean content is 50 milligrams, but we're looking for hard evidence that it's less. Okay, so the way it's written, if the mean is below, then we have a problem that has to be addressed. So that's why it's a left-hand test. Because if the mean is below 50, then we have to make a change. But we don't want to do that unless it's absolutely necessary. Okay, so that's why it's written this way. Alpha is 0.01. Because now the reason why they chose 0.01 is because they need really hard evidence before they do this. It is not going to be cheap. So let's look at the data they gave us. We have 20 cartons. X bar is 48. And the sample standard deviation is 2.4. So we're going to test this hypothesis. Now we can do it in a couple of ways. We can either use, of course, the test statistic and critical values. And remember, now, because this is a single population mean, and we do not know, just a little reminder there, we're going to use T equals X bar minus mu 0 over S over radical N, or 48 minus 50 over 2.4 radical 20, which is about negative 3.73. And since it's the t distribution, what about our critical values? Well, it's actually just the one. And in this case, the degrees of freedom is simply n minus 1. Our sample size is 20, so therefore we have 19 degrees of freedom. And remember, the tail area is only 0.01 because we're trying to be very, very conservative with this one. So you can go to your calculator. And let's see what we get. INDT, area 0.01, left tail is 0.01. And we have 19 degrees of freedom. Oh God, what did I do? Oh, I know, I made a typo, of course. All right, so the test, the critical value rather is negative 2.54, let's say, negative 2.539. Unfortunately, though, the test statistic is negative 3.73. So therefore, we reject the null. And that's bad news, isn't it? Okay, so since the test statistic is in the rejection region, we reject the null that the mean is 50 and accept the alternative hypothesis, the mean is below 50. Therefore, the company will have to use the more expensive oranges. Okay. Or, as usual, we can try the p-value approach. Second vars. Number 2 is t-test. It's a single population, so we use t-test. And when we get there, it's going to ask us for. No, I did it again. It's why do I keep doing that? It's stat tests. Okay, much better. This is one of those days. It must be the weather or something. So of course, then we need to specify the hypothesized value, 50. And it needs to know, oh, make sure it's in the stats mode, by the way, since we were using the list mode a little earlier. Okay, so mu, 50. Hold on. Yeah, X bar is 48. And then it needs SX, standard deviation, which was 2.4. And it needs N, which is 20. Then it needs to know that it's a left-tailed test. And then when you run it, calculate, of course, the p-value turns out to be 7.149. Wow. Which is, the same thing as 0.0007149. So once again, since the p-value is below alpha, we reject the null. The mean is 50 and accept the alternative. The mean is below 50. The company will have to use the more expensive oranges. Oh, well. All right. Well, sadly enough, I missed your chat. Sorry. How do you go from list mode to stats mode? To get out of the list mode, you have to hit second mode. Mode is right next to the second button. Once you've done that, you can go to any other mode you want. All right. I missed that. I hope that wasn't sitting there for too long. So to get out of the list, you have to hit second mode. And then from there, you can go anywhere you want. And for stats mode, just of course, hit the stat test button. All right. Anyone else? So anyway, of course, I'm going to see you all again on Monday, unless something else happens. But even then, we'll be doing this online. I hope that we'll be able to come to school on the 4th, because that's when our test is. But I have a feeling that by then it'll just be a lot of rain all the time. So we'll just wrap up these last few. There's 2, 3, 4, 5, and 6. That's it. So we're very close to the end here. And then we'll be ready for the test on Friday. And then you can relax while we go through chapter 13. And then the following week, I think we're going to have our spring break. No, the week after spring break. Yeah. Yes, you may. All right. Anyone else? All right. I guess we'll knock it off right here. I hope your other classes are online too. I don't know. The school didn't say that we must do it this way, but I thought it was a good idea. So I'll let you go now, and I'll see you all on Tuesday. All right.
Have a great weekend, Professor.
Bye.
Thank you.
Later. Okay, bye.
Oh, hi.
Hi, go ahead.
Oh, oh, okay, sorry. So I have a testing accommodation
Okay.
for time and a half.
Right.
Oh,
So how do you handle that? You can have two options. You can stay in the room longer and continue
Mhm.
until you're done, or you can have it done with a proctor.
Okay. I'm okay with doing it in class.
Okay.
I just had a question.
Mhm.
So if I have a class directly after, do you know what I would do about that?
Oh, see, that's why you might want to think about doing a proctor, because
Okay.
otherwise you'll start to feel rushed and it'll be a problem. So what that means is you would go over to the economics department at some
Okay.
point when it's convenient. I don't know exactly who does the proctoring, but it means that a faculty member or an administrator would basically have you come into their office and do it. Or I don't know exactly where they do it, but you would have a separate room and you wouldn't be in the classroom with us and you wouldn't feel any
Okay.
time pressure, which is the whole point of it. So you could just have whatever time you're allowed, and then what they would do is they would send the results back to me.
Okay, great.
So what that means then is that on that day, instead of coming to class, what I'll do is I'll get a hold of the administration and ask them, to set up a time with you.
Okay.
You think that would work better?
Oh yeah, because I know there's someone
Yeah.
else in the classroom. So
Right. Yeah. Plus,
makes
what's
sense.
going to happen if you're sitting there, the others are going to come in, and no matter how careful they are, they're going to make a lot of noise and they're going to
Mhm.
distract you. So I think it would be easier to just have a proctor.
Okay, great.
Now, on the other hand, there is another option though. I've just started doing this tutorial session on Wednesday mornings, but
Mhm.
then if anyone shows up, there's going to be people in the class making noise. So maybe I'll tell you what, let's just do the proctor.
Okay.
All right. And then here's what you need to do though. You send me an email or tell me again on Tuesday, because I might forget.
Okay, yeah, I'll send you an email.
All right, good. Yeah. And then I'll write to the appropriate people and ask them when this can be arranged.
Okay, great.
All right, great.
All right, thank you.
All
Have a
right.
nice
See you
weekend.
Tuesday. Okay, bye.